everybody, welcome. My name's Jennifer Griffith and I work at NUMOA, which is the Northeast Waste Management Officials Association. We are an interstate association. The 6 New England states, New York and New Jersey, work together. The solid waste programs, the hazardous waste programs, the pollution prevention and toxics reduction programs in the states, and then also the waste site cleanup programs. And the main priority for waste site cleanup programs to do through NUMOA is training. And so that's what we're doing here today. PFAS has been, a big hot topic that's constantly evolving since about 2016. And we've done a lot of webinars and we're doing some more. So today we've got two great presenters. We got Rob Martin from Clean Earth, and then also Rebecca DiStefano from Calgon Carbon are going to be presenting about thermal destruction and different aspects of that today. So we will be posting the presentation PDFs afterwards on the NUMOA website. So that's part of why I have the NUMOA website showing. Rob and Rebecca, do you see the NUMOA website?
Yes.
Yeah. Yes, okay. Good. And so I'm going to just briefly show you where you'll be able to find them later. But also today we've got a lot of people joining, so we will be doing questions. You can type them in at any point, and then I will moderate the questions when we get to that point. So just that, and I'm just going to show, I gotta move my things around here, but the NUMOA website. So you can find information about this webinar as well as other webinars by going to events. So I'm just gonna click on that here. Hopefully it opens, or don't tell me my computer's gonna be really slow today. Wonder why that's not working. Well, here, let's go to this one, which seems to be, guess it's just going to be slow. All right, here's events, and it's very forward looking. So here's today's webinar, and then here's other ones that are coming up, will be down below it. But after today, to this webinar, will be in the past. So to find past events, you have to go, this little secret arrow here, is very key. So you click that, and then you can get to things that have happened in the past. And then it goes the opposite way. So the furthest in the past that it shows in one screen is at the top. You scroll all the way down, and then here will be where today's webinar will end up at the bottom. Here's one we did last week. I'll just show you what it will look like. Click on that, and then you can see the presentations are linked here. Oh, well, that one's not yet. I don't have his yet, actually. That was silly. Okay, well, with that, I will just go back to the NUMOA website. And we are doing, for these webinars, we've gotten Massachusetts Licensed Site Professional Continuing Education credits. And so if you want those credits, again, Massachusetts Licensed Site Professionals only. But if you are one of those and you do need continuing ed credits, there's a few things you need to do. You need to stay on the webinar all the way till the end. You can't be doing other things. This is just a general notice to everybody, but GoToWebinar can tell if you're not paying attention and you're doing other things on your computer. So the webinar broadcast is not the top level of your computer. So you can't, if you want the LSP credits in particular, you cannot be checking emails or sending emails or doing any of that thing. You have to have the webinar at the top of your screen so that you have an attention score that's high. You also are going to need, we're going to insert, and I apologize to everybody else, a few poll questions into the webinar today. And if you want the credits, you definitely have to answer all three of them. But everybody should answer the poll questions just because they're going to be interesting. And also, if you want the LSP credits, you really should type in at least one question during the webinar. Hopefully it's relevant and, you know, interesting that everybody else will want me to ask, but you need to type in. And then if you did sign up for this webinar a long time ago, before I put a question into the registration form, you know, and you do want the LSP credits, you need to email me afterwards and just let me know that. So I think that's most of my logistics. I'll just remind everybody else again that we will be posting the presentation PDFs on the NMOA website sometime later, probably next week. And I will send an email around to everybody once that's done and they're available. And we're going to do questions today in written format. So you have a GoToWebinar control panel on your screen, and there's a questions section. So you type in the questions at any point during the webinar. And I think that is all I have logistic-wise. So I'm going to now introduce the first presenter, and she can get her screen going here. So our first presenter is Rebecca DiStefano. She's a senior applications engineer at Calgon Carbon Corporation in the Industrial Solutions and Diversified Applications Business Unit. Prior to this position, Ms. DiStefano was senior group leader of carbon applications and testing, overseeing testing to evaluate activated carbon performance for PFAS removal. She received her Bachelor of Science degree in Chemical Engineering from Penn State University and her Master's of Business Administration from Robert Morris University. So with that, I'm going to mute myself and stop blabbing and turn my camera off, and you can just focus on Rebecca's presentation. So take it away.
Thank you. I'm going to take my camera off and then I'll share my screen. So thank you for joining today. So today I'll discuss our research on thermal destruction of PFAS during full-scale reactivation of PFAS-laden granular activated carbon. So just a really brief background on Calgon and capabilities and why we care about what happens to PFAS-laden spent granular activated carbon. So Calgon Carbon is a Kuraray company. Kuraray is a Japanese company that purchased Calgon Carbon in 2018. So they are based in Japan. We are headquartered in Pittsburgh, and we have our European branch that is Chemviron in Europe. So together, that is the Environmental Solutions division of Kuraray. Our capabilities, particularly around PFAS and emerging contaminants, include R&D, applications engineering, technical services to be able to define the problem of what is potentially in water or a process stream that needs treatment. So granular activated carbon absorbs contaminate, leaving a purified stream on the effluent. We also have equipment engineering and fabrication capabilities, field service to exchange the activated carbon once it becomes spent, and obviously logistics to move all those millions of pounds of carbon produced. So Calgon Carbon operates both production of virgin activated carbon and reactivation of the spent activated carbon by thermal processing. Last, I'll note our rapid response for spills, issues, fires, problems that need immediate treatment. We have emergency response equipment and carbon available to meet those needs. So next, just a brief, we call it Carbon 101 to give some context to the type of adsorptive media that we're discussing today. So activated carbon is a crude form of graphite. So if you think of graphite, like the lead in your pencil, those graphitic plates slide perfectly against each other, which allows that pencil to write. Carbon is disjointed, imperfect graphite, so it is locked in place. It's not going to slide off like pencil lead graphite, but you think of it in terms of these layers of graphitic plates. So we often hear about pore structure, pore volume, pore size with respect to adsorptive media, and that is a valid term to use, but visually or as a pictorially, it's actually these plates that allow the contaminants to adsorb between the layers of graphite, and the space between those plates dictate the energy of that pore site. So the farther apart, the lower the energy, the closer together, the higher the energy, and different contaminants require different pore energy to adsorb onto the carbon. Different raw materials produce different types of activated carbon. The most common raw materials are coconut shell, and it's actually just the very, very hard shell, not the outer husk and not the meat in the middle, but there's a thin layer of very hard shell that's used for activated carbon. Bituminous coal, lignite type coal, and then wood. Calgon Carbon offers wood, bituminous coal, and coconut products, and all of our US manufactured activated carbon is from bituminous coal. Those raw materials produce products with different characteristics, both from physical property standpoint and from adsorptive properties. The ash impurities are different, the density and hardness is different, the ratio of adsorptive pores to transport pores, so that pore size distribution is very different. So just something to keep in mind when you're looking at activated carbon products. And this is a visual of the graphitic plate representation for those different products. Coconut has the tightest pore structure, the hardest composition. Wood has the most open pore structure and is the softest in terms of physical properties. And bituminous coal allows for kind of a balanced, open enough pore structure to allow contaminants to get in, but tight enough in certain areas to hold on to a high amount of contaminant. And now we'll start the discussion on PFAS. So Calgon Carbon's been treating for PFAS removal for over 20 years. We're effectively able to achieve with our equipment and carbon product solutions non-detect levels down to the current MCL part per trillion level requirements. We have over 150 full-scale installations for PFAS removal across the United States at this point. So used in drinking water, industrial wastewater, remediation, point of entry type systems. We have laboratory and field testing to be able to run scale down simulations of our activated carbon systems to predict performance and demonstrate efficacy. With our reactivation portion of that, where the carbon is removed from the application, the vessel, and returned to us for thermal reactivation, it's the complete solution relative to closing the loop of where the PFAS goes and what happens to it after removing it from the environment. This is a demonstration for treating lab scale versus our full scale installation. So lab scale on the left is showing bed volumes treated versus our PFAS concentration for 6 common PFAS compounds, C4, C6, C8, so PFOA, PFOS, HXA, HXS, PFBA, and PFBS. On the right is our full-scale Model 10 system, which is a 10-foot diameter vessel with 20,000 pounds of granular activated carbon, operated with 10 minutes of contact time. And you can see our lead vessel in blue is just starting to show breakthrough of PFOA. a little before 300 days of operation, and our lag vessel would be the second vessel in series, is non-detect. The second lab study demonstrating effectiveness for the current primary drinking water, MCLs. So we had starting concentrations for each of these compounds at 200 part per trillion, and our FiltraSorb 400, simulating a vessel with 10 minutes of empty bed contact time, is removing our PFOA and PFOS to below the 4 part per trillion target, Gen X below the 10 part per trillion target. And the other important thing to note on this chart is that these compounds do adsorb differently. The shorter chain compounds are more difficult, they break through sooner. So treatment is possible. They certainly are still removed by activated carbon, but there are differences based on the compounds that are present, the concentration of those compounds, and also background TOC. So proper testing, proper design, and interpretation of the test data is very important when you're trying to understand and simulate a full-scale carbon system. So as water treats a contaminant and the contaminants are adsorbed onto that filtration media, GAC, ion exchange, or an activated clay, clean water is released out of the effluent. But when that media has met its capacity, it's important to understand what the next step is, what happens to the media and what happens to the contaminants that have been adsorbed onto that media. So with respect to activated carbon, there's a relatively unique solution called reactivation. And reactivation is the thermal process where the carbon is physically removed from the site of treatment, transported back to a reactivation facility that is permitted to handle spent carbon, and then a new reactivated product is produced. And that product can then be utilized in additional wastewater treatment at other sites. Other types of media, ion exchange or clay-based adsorbents, don't necessarily have this option. It requires either incineration or landfill, often more costly than reactivation. So at this point, the reactivation process, we're able to provide certificate of destruction that the adsorbed materials have been handled appropriately within permit limits, and both CERCLA and RCRA facilities for processing of those types of carbon are available. There are no landfill liabilities associated with reactivation of spent carbon. Relative to the production of virgin carbon, there's an 80% reduction in CO2 emissions. So this is a sustainable process that allows us to utilize activated carbon most effectively and to continue to recycle until that carbon can no longer be used. In general, reactivation is lower cost relative to incineration. And carbon reactivation was recently recognized by EPA as a disposal method for PFAS-laden activated carbon. So there's interim guidance for destruction and disposal of PFAS waste or PFAS-containing sorbent materials, and reactivation is specifically cited within that document. Also, in June 2023, the Department of Defense had previously issued a moratorium on incineration of PFAS-laden waste products. In general, that did not apply to activated carbon because we are under a different CFR, Code of Federal Regulations, compared to waste incinerators, but it did cause a good bit of confusion at the time. So it was important to note that in that memo, it was specifically stated that reactivation of PFAS-containing GAC was an option for handling PFAS contaminated or PFAS-laden spent carbon. In terms of reactivation sites and capabilities, Calgon Carbon operates 5 sites in the US. 2 are RCRA facilities, 3 are potable, and of those 5, 4 of them are also CERCLA approved. There are 2 sites in the United Kingdom. We have the world's largest reactivation site in Belgium, and then also 2 sites in Europe. Millions and millions of pounds of activated carbon are reactivated every year, and over 30 years of experience with these processes globally. So to review what is actually happening to the activated carbon as it goes through the process, I'm showing here a picture of a multi-hearth furnace, and you can see people working on that furnace, and about one level where they're standing is probably like 1.5 levels or hearths. So it's called multi-hearth because there are different levels to it. And the carbon works its way from the top of the furnace down to the bottom in an inside-outside type of pattern. The top of the furnace is at the lowest temperature, and that's where the any water is driven off of the carbon. From there, the temperature starts to increase on that first hearth, where thermal devolatilization and desorption can occur of very lightly low molecular weight, low adsorbed compounds. At higher temperature, there's pyrolysis and calcination chemistry happening. And then as we reach the higher temperatures, 800 to 1000 degrees C, in the presence of water or as steam, gasification reaction occurs where the carbon is actually activated similarly to conditions of producing virgin activated carbon. So the goal of the reactivation process is obviously to remove and destroy contaminants, but also to produce a high quality carbon product at the end. So it's important to note that there's no combustion happening. We don't want oxidation of the activated carbon. We don't want burning because that's going to impact the quality of the product at the end. If you burn out your carbon, you're losing adsorptive capacity, you're lowering the density, and you're making it more susceptible to abrasion or physical breakdown. So again, the chemistry involved within this furnace is significantly different compared to an incinerator or an afterburner. One very important component of a carbon reactivation program is carbon acceptance testing. So the majority of spent carbon can be taken back to a reactivation facility, but in some cases, we do have to reject that spent carbon if certain criteria are not met. Carbon acceptance is to ensure the safety of the environment, our plant personnel that have to physically work and handle our spent carbon, process equipment susceptible to corrosion or other problems, and then obviously, as I stated before, the quality of that reactivated product. So with those goals in mind, regulatory compliance, safety, we have multiple tests that are required and documentation that's required when carbon comes back to our facility. That includes the density of the carbon, pH range of the carbon, whether or not it is ignitable, the actual nature of the spent relative to sulfur content and halides. Does the carbon react with water? What is the percent moisture? Ensuring that it is not radioactive, which unfortunately does happen. The level of inorganics that may form an unacceptable level of ash or may act as an accelerant in the furnace. And then ultimately, can the spent make a proper quality in terms of the reactivated carbon? And then specifically for liquid phase applications, ensuring levels of lead, mercury, or hex chrome do not exceed regulatory limits. and then monitoring the BTU content for RCRA hazardous spent carbon. So just a bit more on incineration and regeneration relative to thermal reactivation. So the United States CFR defines an incinerator as any enclosed device that uses controlled flame combustion and neither meets the criteria for classification as a boiler, sludge dryer, or carbon regeneration unit, nor is listed as an industrial furnace or meets the definition of infrared incinerator or plasma arc incinerator. So from that definition of incinerator, carbon regeneration unit, which is confusing because we would say reactivation as opposed to regeneration, it is classified differently. So a carbon regeneration unit, reactivation in Calgon Carbon terms, is defined as any enclosed thermal treatment device used to regenerate spent activated carbon from Hazardous and Waste Management 2022. So from those definitions, it is classified different from incineration. It's a different chemistry happening within the thermal treatment device. And again, there are different objectives between those two systems. So from Calgon Carbon's perspective, regeneration is defined differently. When we're speaking of regeneration, it refers to a process that's typically done in process on the site. The carbon is not removed from the vessel, and either changes in temperature, pressure, or addition of chemicals shift the equilibrium so that the adsorptive properties are changed, so that maybe you're adsorbing under conditions that allow for the highest capacity, and then you change the operating parameters to desorb a certain portion of the adsorbed contaminant or the working capacity of that carbon, and then you continue that process in perpetuity, basically. And the effect of that is you start with your virgin carbon, you load its capacity, then you implement your regeneration step. That regeneration step is typically at lower temperature or at a shift in conditions that is still going to leave some of that contaminant on the spent carbon. So you're basically not removing it fully, you're just utilizing the difference between the regenerated capacity and the spent capacity to recover whatever contaminant is being adsorbed. So again, the in-process steps can be solvent recovery system, where you're actually trying to conserve and reuse solvent on site, or things of that nature. Reactivation, the objective is to operate at a high enough temperature where you are desorbing fully and returning that carbon to a virgin-like state. So contaminants are either removed or charred in place and transformed from their adsorbed state, so that you get a high quality and extremely clean reactivated carbon at the end. So the temperature range and the operating conditions are drastically different between reactivation and regeneration. And I think here we will pause for the NOMOA poll question.
Okay, let's see if I can get this to work here. Let's see. Okay. Here is a true or false. Carbon thermal reactivation is a completely different process than incineration or carbon regeneration. So please vote, everybody. And if you want the Massachusetts Licensed Site Professional continuing ed credits, you must answer. But everybody else, voluntary. We'll see if a few more people vote. Let's see if we can get up to 80% of people voting. Can't see how people are voting. I just see the percentage of people on. Okay, I think that's long enough. I'll close that. And Rebecca, please talk about the answer, which is true, I believe.
True. So as we discussed, carbon reactivation is a unique process different from incineration and regeneration, both objectively and based on the process conditions and operations. Okay, so this is the, I would say the last section of the presentation that is devoted to the research on the reactivation process and PFAS destruction throughout. So as I had mentioned before, we have a multi-hearth reactivation furnace where carbon enters the top and is discharged out the bottom. The furnace off gas is then treated through a thermal oxidizer, chemical scrubber, bag house for particulate removal, and then exhausted out the stack. So to conduct this study, we used the best commercially available analytical for PFAS testing. We had to look at solid, liquid, and vapor phase analyses. We have samples of spent carbon and reactivated carbon. The spent carbon is really the defined input to the system. So your destruction calculation is based on what that feed rate is. And then in vapor phase, we utilized OTM 45 at the furnace outlet, so between the furnace and thermal oxidizer, and then at the stack. We also tested the bag house or abatement dust by solid extraction for PFAS, and liquid analysis of our cooling water. The results of this study, so the study was conducted in 2021. The results were published open access in the Remediation Journal in 2022. So those are available for anyone to review the details. So I'll just now give kind of the highlights. Looking at our spent carbon and our reactivated carbon, the quantity of PFAS that was extracted and analyzed, significantly different. So this is in nanogram per gram, which is part per billion. And you can see we're at right around 100,000 part per billion on the spent carbon, and we're non-detect on the reactivated carbon. So demonstrating that those PFAS compounds are removed from the reactivated carbon during the process. We did have one hit of a perfluorooctadecanoic acid. We retested, and then that also came back non-detect. Obviously, I think anyone familiar with these types of tests is familiar with the challenges of these very, very low detection limits. But this data is showing that even at these extremely high feed loading values, we're able to achieve removal from spent or from the reactivated carbon. Looking at the vapor phase relative to the solid phase. So taking those compounds, 29 compounds on the spent carbon that were analyzed, 36 compounds in the furnace off gas. There was really nothing in any other input or output, the cooling water, the abatement dust, that impacted these numbers and was detected. So we have about 0.75 pound per hour PFAS coming in on our spent carbon in the system. Our furnace off gas was 8.4 times 10 to the minus 5 pound per hour for a total destruction removal efficiency through the furnace of 99.989. We saw additional removal through the thermal oxidizer for a final value of 4.88 times 10 to the minus 5 and an overall DRE of 99.993. So we're able to demonstrate destruction and removal efficiency for these targeted compounds at greater than 99.99, with the majority of that destruction occurring in the reactivation furnace under those unique reactivation conditions I mentioned, and then polishing occurring in the thermal oxidizer. Finally, one of the major challenges, I'll say, for the industry or anybody working on PFAS destruction at this point is fluoride measurement and attempting to close the fluoride mass balance. This is obviously just a challenging field in general, given the reactivity of any hydrogen fluoride that is produced. and also detection limits for total fluoride on solid samples in vapor phase. Really, if you achieve non-detect somewhere based on that detection limit, it might not actually be very informative because you still can detect part per trillion PFAS. But in looking at our values, we are able to detect some total fluoride as measured from the spent carbon within the reactivated carbon and abatement dust and within our furnace off gas. And our fluoride mass balance able to be close to about 61%, with the majority likely being very reactive within that furnace lining, the process equipment, and anticipated low recovery from those abatement dust and potentially the vapor phase analyses. But again, as methods improve, detection limits improve, it is important to define and attempt to close that mass balance as much as possible. So finally, our conclusions and key findings. Calgon's reactivation process is a unique process that thermally removes PFAS and achieves high destruction in the reactivation furnace through a robust abatement system. Reactivation is very different compared to incineration or regeneration. Our proprietary process was able to achieve greater than 99.99% destruction for the targeted PFAS measured. High level of hydrogen fluoride detected supports mineralization of these compounds as the source of the fluoride in the HF measurement. And reactivation is well established, fully commercialized, safe, simple, and effective technology for removing PFAS from the environment. In addition, it's a sustainable process that allows for recycling of activated carbon and has 80% reduction in CO2 emissions relative to virgin carbon production. So with that, I have our contact list up there, our website, and I think our PFAS landing page is given there. So thank you very much, and I'll be happy to answer questions.
Great. Well, thank you, Rebecca. And yes, there are quite a few. So let's see. There's a lot. So probably not going to be able to get through all of them, but I'll ask this one. How does a record classification of PFAS and PFOA or any of these regulatory developments impact the ability of granulated activated carbon to be returned for reactivation?
So at this point, because we do have two facilities that are permitted to handle RCRA, there's no impact to return of carbon there, but there is potential impact for drinking water if that is not exempt. So right now, there are basically two different paths for reactivation depending on the objective. And as I mentioned, we have potable sites, and potable sites operate with our municipalities to do custom reactivation. So the municipality returns their carbon, we reactivate it in a batch process and return their same carbon back to them with some virgin makeup. Industrial reactivation takes everything back into a pool, and we get a final reactivated carbon at the end that's used for wastewater treatment. And that is the RCRA type of reactivation process. So we can still process RCRA carbon, but there would be implications for that custom reactivation for drinking water. So in that case, in my opinion, the hope is that that will not be the direction regulators take. We want drinking water to be not classified under that category for drinking water spent carbon.
Okay. Of the granulated activated carbon that you guys have out in commerce here, what percentage of that is used to treat PFAS is eligible for reactivation? Are there like influent limits that you have, or is there any limitation on what you can take?
So there is a fluoride limit on what we can process through our furnace. There's some capability to mix and kind of blend as we feed to reduce those limits. And typically in water treatment, those limits are not exceeded for fluoride. It's very rare. In vapor phase, however, the capacities are significantly higher, and that becomes a bit of a challenge. So, figuring out how to either operate to keep the loading at a reasonable level that can be reactivated, I would say is the primary concern. But typically liquid phase applications, really we aren't seeing loadings high enough, especially if anything with drinking water, nothing's high enough that's rejected based on fluoride.
Okay. So it just in general, I mean, I think the reactivation process, does it generate a significant amount of material that needs to be disposed of? I know there's, the air emission treatment system is going to generate some water and some solids, but, in the scheme of things, how much is that? And are there other contaminated materials or, and what happens to those things?
So it really is the vapor emissions, stack emissions, and then abatement dust or particulate dust, which is not hugely significant relative to the quantity of carbon produced. So it's just the ancillary dust from the chemical injection into the scrubber as it neutralizes acid gas produced in the process. But otherwise, no other waste streams.
Okay. Let's see what else. Well, I guess there's just the basic question, which I have as well, which is how do you even make activated carbon from the beginning? Like, can you explain that briefly?
Sure. So I'll speak to bituminous coal. There's little variations on the different processes based on your starting material, but with respect to bituminous coal, Calgon Carbon produced what's called a reagglomerated product to ensure that it's uniform and it has good physical properties and it can hold up the granular integrity. So you start with coal that's then pulverized into basically powder. That's what we call briquetted, so kind of smashed together in these little maybe 2-inch by 1-inch oblong type briquettes is the term. Those are then crushed and sized to the target size of your activated carbon. So typical mesh sizes are 8 by 30 or 12 by 40 for water treatment. That coal powder that's been compressed and then granulated has to go through 2 different thermal treatment steps. The first one is carbonization, which fixes the actual graphitic plate structure of it and devolatilizes and oxidizes all of those coal volatiles. And then after going through that carbonization process, it's the activation process, and that utilizes steam and much higher temperature to impart the activated carbon surface area by removing carbon molecules. And we say gasifying, activating, but that's what creates the actual internal pore structure, pulling off carbon molecules within that graphitic plate structure. So it's a matter of defining first the physical part of it, getting the granules, and then carbonizing it to fix that structure, and then activating it to create surface area.
Okay. I think we'll do one more and then we'll switch over to the next presentation. But can you talk a little bit about the typical client, say a water treatment system? Are they regenerating or reactivate? Like how do you figure out whether you should regenerate, you should reactivate? Is that a standard service that you're providing? Is there a big cost difference?
So reactivation is a standard service. Pretty much any time we do an initial, project to do treatment, we include carbon acceptance as part of the initial proposal, so that we want that carbon to come back. We want it to be recycled, and we want to make that reactivated product because that has value. That's a separate product that's actually sold for wastewater treatment. So I would say it's pretty much industry standard at this point that if you're going to utilize activated carbon, you would want to reactivate it. And typically the cost associated with reactivation is the freight required to return the carbon to one of our sites. So, a fraction of installation of virgin carbon.
Is there a limit to how many times carbon can be reactivated?
Way that we operate, so from a chemistry standpoint, probably yes. At some point, you will pull off enough carbon atoms that the structure cannot be maintained, and you'll have that carbon, kind of fall apart on you. But from a practical standpoint, we really don't see that for custom projects. Every time that comes back, if there's some physical losses, yield losses, whatever, a percent of makeup carbon is added to try to keep it at basically a steady state in terms of the quality for the carbon that's recycled to one specific location. On the kind of industrial RECRA pool react side, all different carbons are coming from all different customers and going through, and the goal is to have a relatively consistent quality at the outlet. So in terms of number of cycles, it's not really tracked. So I think if you did it in a laboratory setting, somewhere between 10 and 15 reactivation cycles is where the number of atoms becomes just too small to hold the particles together. But from a practical standpoint, not really.
Okay, one last question. It was kind of a global question, because now that the MCLs are so low, and so many more people are going to need to treat, and you showed us the sort of breakthrough slides, and at the really low levels, they're going to have to change things out more often. Is there enough carbon out there, and you guys have the capacity to be servicing all this stuff?
So we absolutely think that there is. We're well aware, and that question comes up very frequently, actually. So we just completed an expansion at our plant in Mississippi, and I think everybody at Calgon is keeping their eye on kind of those projections and where things are going in terms of reactivation capacity and virgin carbon production capacity. But right now, yes, we have plenty of carbon.
All right, well, on that positive note, I'm going to switch it over now to our next presenter. There were some more questions, and we'll get to them at the very end if we have time. So our next presenter is Rob Martin. He's a member of the Thermal Desorption Treatment Technologies Group at Clean Earth, which is based in Fort Edward, New York. Well, he's based in Fort Edward, New York. He's helped develop the PFAS research, development, and demonstration permits, RD&D permits for New York State, DEC, and the successful completion of their first PFAS contaminated soil and compost project. And let's see, he's been directly involved with thermal treatment of 2 million tons of soil at a fixed facility location and portable treatment operations. Project soil contaminants included asphaltic materials, conventional fuels, creosote, energetics, explosives, manufactured gas, plant waste, PCBs, pesticides, and PFAS. So he's got a lot of experience with thermal desorption of all kinds of contaminants. And with that, I'm going to turn it over to Rob.
Thank you, and thank you again to all those who are in attendance this afternoon. By title slide here, you'll notice that this presentation was actually made at the Northeast Conference on the Science of PFAS. A few changes to the slides themselves, but for the most part, the content is very consistent.
Oh, Rob, you muted yourself. You're muted.
Yeah,
There we
I
go.
apologize. Sorry. Yeah, just a quick presentation outline. Review of thermal desorption technology, clean earth research projects, which you're involved in with ourselves and those in partnership. A little bit of information on the thermal desorption industry and what others are actually doing to advance the science in relation to the treatment of PFAS. And then some developing PFAS destruction science review, and then a few other information resources in relation to thermal desorption. As you know, this presentation has a lot of reference documents that are cited. All the slides, once it's posted out, will have links on each particular page that will take you to the individual referenced items. Some of them, since they're science documents, you do have to pay to get access to, but most of the stuff I've been trying to find is via open access. So a little discussion on thermal desorption. On the right-hand side is actually a EPA document, Community Guide to Thermal Desorption. A quick note in relation to Clean Earth, specifically the actual picture of the thermal desorption unit. In the lower right-hand corner is Clean Earth's mobile thermal desorption system. This is a picture actually of it sitting on Cape Cod at a military installation. But to discuss the technology itself, thermal desorption, I always like to liken the technology to your clothes dryer. Everyone's generally run a clothes dryer at some point in time. But you know, it's a rotary kiln, very similar to your dryer, where the material is lifted and tumbled, and a hot air stream is passed through with the intent of, you know, in relation to your clothes dryer, removing the moisture or the water. But from a thermal desorption standpoint, from a contaminated mass treatment, we do the same process. We take and we boil the water off of the soil, and then heat that soil, which is now free of the moisture, to a point in content where those contaminants are evaporated or boiled from the soil mass itself, leaving a soil mass that is relatively clean or clear of contaminant. Once those contaminants are evaporated, turned into a gaseous state, they're then transferred to a system which is thermal oxidation. So with our particular units and the way that they're designed, the material is carried to a thermal oxidizer, where the basic chemistry associated with it, just in general, converts those contaminants to carbon dioxide and water. Now, in relation to PFAS, as was just presented also by Calgon, that those, you know, you do generate HF as an off gas from that particular treatment process. Also, as previously presented, you know, and as actually listed here in this community guide, thermal desorption is not the same as incineration. You know, just two big differences in the technology. The way Clean Earth deploys the tech, all the soil most of the soil that's treated via our thermal desorption technology actually gets put back into the environment as beneficial use material. So we have facilities where we can treat soils, including coal tar contaminated soils, put those back out into the market as a sellable fill material, which can go to residential sites. Second difference is, you know, the feedstocks going into these systems are relatively low in concentration to what could be potentially fed to an incinerator. You know, where incinerator could feed, you know, AFFF just as a liquid into it, we cannot treat, you know, 3% contaminant loads in these particular technologies. They're not designed for that. And most of the time we're talking about, you know, parts per million concentrations of various different compounds, you know, could be double or triple digits depending on what the contaminant is. But, you know, two big differences there. One, the beneficial reuse of the soil post-treatment, and two, just the mass of contaminant that's actually fed to the systems. A little bit of a process flow diagram itself. Just pull up a pointer here quick. So in a thermal desorption system, there's really only one part or process unit that actually does the soil treatment, and that is actually the rotary dryer or rotary kiln. So where the soil is fed into it, exposed to that high temperature, you know, being tumbled or rotated through the system, and then it's discharged out and then cooled, and then you end up with a pile of treated media. All the rest of the technology is really to help control the process airstream. So the outlet airstream from the rotary goes through a cyclone to remove any sort of dust, so that we're then oxidizing a relatively clean airstream. Post-oxidation temperatures, that airstream is then cooled through an evaporative cooling chamber, which uses an air over water system to generate a very fine mist. And the steam that's generated from the heat being added to that mist water cools that airstream down so it can be finally filtered via a baghouse particulate system. And then the clean gases are exited out through the through the stack. The technical paper, this T125 document, it's a document that was produced by Aztec Industries. Some of you may be familiar with Aztec from their design and build. You see their name on quite a few asphalt plants, but they also in the past have generated thermal desorption units in of themselves. So, oh, sorry. Research projects. Clean Earth ourselves, as was mentioned in 2018, partnered with New York State Department of Environmental Conservation and provided and completed a test on some PFAS contaminated soil that was identified within the state. You'll see here just a little bit on the soil data itself. It was 22 tons of soil. Important point to note, because our systems can process up to, and on average, around 35 tons per hour. So the amount of soil that was really put through the process itself is relatively small and did not necessarily allow for any sort of real additional science to be completed other than what our base premise was. It also did not allow us then to complete any sort of emissions testing on the unit itself during this particular operation. The source of the soil was an asparagus farm. They were taking in organic matter, soil composted organic matter. That composted media was actually the sludge associated with a secondary paper fiber facility within the area. And that's where the actual PFAS was being moved to the soil from. Just a little bit there on what PFAS moss was in the soils itself. On the permit criteria at the time, New York State had what they had a clean fill criteria. And at the time, their criteria for PFOA and PFOS was a 72 part per billion as an additive of the compounds, and that the soil SPLP had to be less than 10 part per trillion. And if you met that, it would be clean fill, and that was the criteria that was set in order for us to be able to have a successful research project. In relation to the oxidation temperatures at the time, and this is a little bit important too, there was an EPA technical brief out on the oxidation of PFAS. And that's why I put in the date of 2019, because in that document itself, it references 1800 degrees Fahrenheit as an oxidation temperature. But if you do look up any sort of newer EPA technical briefs, they actually had removed that temperature reference. So a little bit on the results. We did actually end up returning or treating this material twice. As you will see, as we talk about here, in relation to the total PFAS itself, concentrations, which this was done by 537 technology, and they're analytical at the time, we were able to get the soils down to, in parts per billion, 7.76 part per billion. And we were able to reduce what was in parts per trillion, the leachates down to 20.45. What you'll also see is that most of that mass was really associated with PFOS in particular. One important note we had found is that we know that the technology itself does not get rid of all the organic matter, but we did have a significant reduction in organic matter based on our operating temperatures. So we decided that we would try to run this material again to see if we could actually meet the criteria that was set forth by the research project. Upon that second test run, we were actually able to get the totals analysis and all the SP analysis down to non-detect. There was a slight difference in the organic matter concentration that was removed, but we're not exactly certain if that PFAS that was still remaining in the soil was bound to some small fraction of the soil organic matter that was left. But that's something we're hoping that we can demonstrate through some future work at our particular facilities. Some of the future projects and stuff that we actually have that we're in process with now, we're actually performing a R&D project on the stabilization of soils that are contaminated with PFAS by amending them with a commercially available product and determining whether or not we can actually reach leachate concentrations that are in the drinking water range. Thermal desorption, we have a full-scale project that we're going to be working with. I'll talk here in our second on, but we're also working with various Northeast states and attempting to generate other R&D projects at our fixed base locations. As far as the water, we do have water treatment systems. We do have a permitted water treatment location in Detroit for PFAS. We are partnering with Arcadis and supporting various technology vendors in a Defense Innovation Unit demonstration project, where there's destruction technologies that will be destroying concentrates that were generated from groundwater at 2 DoD facilities. And just as a shameless little plug, we're always looking to engage partnership-wise with stakeholders, whether it's at federal, state, local agencies, or even at the private level, in order to help further the tech and develop additional science. Partnership projects. We are the equipment and technology provider for ESTCP project, which is actually being run by Frank Barenko. You'll see his contact information there on the right-hand side. He's with EA Engineering. This particular research project is the placement of the unit, which you see there in the picture, at a DoD facility where the intent is to treat PFAS contaminated soil that has PFAS concentrations could have PFAS concentrations in the double-digit part per million range, for not only testing the soils pre and post treatment for removal and beneficial use criteria, but also the evaluation of emissions from the stack of the unit. Testing is going to include OTM 45, OTM 50, OTM 55, and other testing criteria to help demonstrate if there is any sort of chance of developing a mass balance in relation to HF and fluorine. This is actually built off of a CERTA project that was completed by EA Engineering in partnership with a company by the name of TDX, where they indirectly heated PFAS spiked soils and ran it through a thermal oxidation system post. Just showing some general results here of what they had found from their totals in relation to soils, and then information here, demonstration testing on the stack, and some relative experimental errors associated with them working to generate their fluorine balance methods. So just to review a little bit what the ESTC project demonstration test is going to be, again, looking to demonstrate 99.99% DRE related with the off-gassing emissions, looking at total organic fluorines and trying to determine whether or not they could close up their mass balance gap, which they had from their CERTA project, looking at products of incomplete destruction or combustion, depending on what tech you like to discuss. And then, is it a cost-effective technology in relation to other disposal methods out there? And I'll pause quickly for our poll question.
Yes, and I also realized after you started, I forgot to, there's one I should have done before you started talking. We'll do that at the end, I guess. But here, yeah, I forgot. Here's the question. When evaporated contaminants from thermal desorption are destroyed in a thermal oxidizer, are they converted to CO2 and water? Please select one, yes or no. And we'll see if we can get up to similar number of people voting as last time, or percentage of people voting. So keep going, particularly if you want the Massachusetts Licensed Site Professional Continuing Ed credits, you must answer. So don't forget. And see if we can get a couple more people. All righty. So Rob, talk about the answer here.
Answer is yes. As kind of noted, the general chemistry associated with oxidation of organic compounds is that they're converted to carbon dioxide and water.
Yes, but it's not only carbon dioxide and water though, right?
No, that's why I was trying to make it basic general chemistry in relation to, because, if you are, any sort of chlorinated or fluorinated compounds, you will have the generation of HCl or HF that is associated with that oxidation process.
Okay, carry on.
Fair enough. Some industry data, presenting some information here from ASRC Energy. They're actually based out of Alaska. They have a permit for the treatment of PFAS contaminated soils. They also have a mobile technology. You'll see a picture of it. There's a small picture here in the upper corner. You can see here it's sitting inside of a structure, so a little bit smaller tech than what it is that I showed you, but they're in the process of generating some science in relation to PFAS treatment and emissions. As I asked for information, they just asked that I present a little bit on their company themselves. So they run the same sort of process we do, where they treat thermal desorption, and then they do thermal oxidation. So they do a rotary kiln, which is actually heated through an electric induction process. And then they have a thermal oxidation system, which they can either fuel off of liquid fuels or a plasma reactor. So treatment rise, it's a little bit smaller. It treats about 70 to 80 tons an hour. So they have completed 3 projects, and they are also working on a DIU ESTCP project this summer, where they are treating some contaminated soils, and they're also going through the stack testing protocols, which I had mentioned just a little bit earlier in relation to the tech. So, but some of the results that they've seen to date, in relation to PFAS compounds in the soils, they're generally seeing that they're getting to non-detect treatments levels, somewhere around the 0.2 part per billion range in relation to 537 methodology, which they're presently using. A little bit on the HAP side, or the HF emissions that they're analyzing through their testing process. They're generating very little, about 0.03 tons per year, which is a short cry from what is allowed in relation to the federal HAP numbers. And then they also, through the technology, they don't generate any secondary waste streams. The waste streams that come out of thermal desorption are the treated soil, solid media, and then the effluent gases themselves. So, but again, a little bit difference in the technology. They generate somewhere between 50 and 80 tons on a daily basis of treated media. So, but more to come from them, as like I said, they're deployed on a project presently trying to develop additional science information. So, a little bit more on the PFAS destruction side. For those of you who may have seen it, EPA's Office of Research and Development completed some work. It was entitled Combustion of C1 and C2 PFAS, Kinetics Modeling and Experimentation. This table is actually drawn directly from their presentation. It's their write-up itself. And just wanted to generally highlight a few different items here. One of the things that they were looking at was trying to develop PFAS-like compounds, or fluorinated compounds, that they could use potentially as surrogates in relation to PFAS destruction, because for all these PFAS compounds that are out there and having to generate analytical for all of them, is there a way that maybe some of these can be used as surrogates? So they looked at CF4, as you'll see here, and the only real time that they get any sort of high removal efficiencies, and they could get the CF4 down to a pretty low concentration, not read any sort of have any high readings, was actually injecting it with a fuel gas to their rainbow furnace. So, CF4 itself is interesting from that standpoint. CHF3, when they started to look at it, I'm just going to pump through these because what you end up seeing as you look down through this table is that you end up seeing some non-detects down here in this 2000 degrees Fahrenheit, which is right around some of the science that's out there. But what really starts to become of interest is that once you're in that 1700 degree Fahrenheit range, on some of these compounds you actually are generating less PICs. So you'll see here with CHF3 that there is actually no CF4 that was generated. And if you're looking at C2F6, which during the document they say may be a suitable surrogate in relation to PFAS compounds itself, there is actually less CF4 generated. So at lower temperatures, you're getting higher HF conversion and you're getting lower PIC generation itself. So just something for thought process. Also, which come out of Triangle Park, low temperature thermal treatment of gas phase with calcium oxide, and actually presenting another next slide here as well. But one of the things that they had done is they had taken and lined a furnace reactor with calcium oxide and then had placed and run PFAS-laden airstreams through them. And one of the findings is that they could actually lower the oxidation temperature of the PFAS compounds when they were in the presence of calcium oxide. So obviously full scale, this sort of technology needs to be further evaluated and analyzed, but it actually presents some promise for the fact that there are additives to gas streams or even potential systems as ours that could help reduce the oxidation temperatures, which would make the systems more efficient and make it a little more reasonable to manage. Additional work that was done along the same lines, this actually had come out of Notre Dame University, where they took PFAS-laden GAC and with and without additives, as you see here in the picture, exposed them to relatively high temperatures to determine what sort of PFAS mineralization that they would receive. And with additives, which was a calcium oxide again product, they were able to demonstrate that they could get a much higher mineralization rate than they could without the addition of the product itself. So demonstrating that there is further potential for the enhancement of the oxidation process with the utilization of an additive such as calcium oxide. Another little interesting tidbit with this particular project, Nathan Weber, who's the first name on this, he now is actually part of the ORD research group down in Triangle Park. They did some research where they're evaluating the presence of water in relation to PFAS degradation at various particular temperatures. And what they had come to find is that in elevated water vapor, excess water vapor within a particular thermal oxidation process, that they were able to again reduce and get higher mineralization rates of PFAS-laden airstreams. So not only has it been shown that potentially having excess water vapor in the process, generating some free radicals, also helps to decrease thermal oxidation temperatures, but also the addition of calcium oxide is being shown to help in the particular process. So additional references, sources for thermal desorption, anyone interested? The Interstate Technology Regulatory Council has generated several documents which talk about specific thermal desorption project types and how they should be regulated. That's information's out there on their particular website. Clue-in, Federal Remediation Technology Roundtable, and then obviously the Clean Earth website has some information in relation to the technology itself. So I'll pause. Questions, my contact information there, and thank you for everybody for their time today.
Okay, great, Rob. Well, thank you. Yes, there are a bunch of questions, but before we do that, I'm going to do this other poll question that I meant to do in the middle between the two presenters. But hopefully this is easy because you guys have been staring at his slides. Where does Rob Martin work? This was supposed to be right after I introduced him, but forgot about that. So US EPA, CDM Smith, Clean Earth, or Calgon Carbon. Again, if you want those Massachusetts licensed site professional continuing ed credits, you have to answer. Hopefully everybody else can. And look at that, people voted and everybody chose the correct answer, which is that he works at Clean Earth, obviously. So, all right, great. So what kind of testing are you doing to check whether you're just sort of transforming, particularly the thermal oxidizer with the vapors there, is not just transforming into like the ultra short PFAS or whatever, that we're not just, that you're, how are you verifying that you're really destroying it?
Sure. Well, with what's available for the technology at present from an analytical standpoint, which is really OTM 45, 50, and 55, along with running analysis for fluorine and HF, at the SAC to determine if there's any sort of conversion balance that can be generated.
Okay. Let's see, you had shown the Clean Earth testing between the 2018 and 2019 results, and I think I just want to clarify, the 2018 was, the test was on some more contaminated soil material, and then you took that soil after it was treated, and that's what the 2019 test was on, the treated soil. You treated it again.
Correct. Yeah, we wanted to determine whether or not that the PFAS mass that was still being shown analytically was just bound so tight to the soil or something in the matrix that it wouldn't be released, or determine whether or not we could actually take and remove that mass from the soil itself. So, and one of the difficulties was, again, that we had a very short window of operating time, and we only ran the soil at a single individual temperature. So we didn't have the ability to either ramp up the temperature or change that operating parameter to determine if we could, with a large mass of material, if we had the ability to change those temperatures to determine if we could actually have that soil be remediated just on a single pass run.
Okay, so what's your current thinking? Is that you can do that and you can do a single pass, or that you should, do things twice?
No, the current concept is that that material could be run through in a single pass and meet current beneficial use criteria. Actually, the results from that first pass under current New York State guidance for PFAS actually would meet a residential reuse criteria. We just did not meet the particular criteria for the state at the time.
Okay, let's see. All right, so how about, is there any, so you're treating the soil with thermal desorption, you're treating the off gases with the thermal oxidizer. Is there waste material that's being generated from the system, or does everything turn out, you don't have waste that you got to deal with?
There are no other, there's the only two effluents that come out of the process are the treated soil and the effluent airstream that is exhausted out the stack. So we do not generate any sort of ashes or, baghouse fines. All of that material gets recombined and is part of the soil matrix that comes out of the what we call the back end or the discharge part of the technology.
Okay. Someone's asking if you're aware of any projects that are happening or have happened in Southern California, just whether there's already been permitting, successful permitting that's happened or not in California.
In California, not that I'm aware of, no.
Okay. Let's see. What else do we have here? So what is your thinking in layman's terms of why low temperature with that calcium substance seems to work better than high temperature? Is there some thought there?
Well, I would say if there's other reference documents as well out there in the science realm that are showing that calcium having basically acting as a reaction base for degrading the fluorine carbon compounds under that higher, little bit elevated temperature profile. Specifics on it, if you know, and how that correlates, the work that was done, by EPA and through Notre Dame was, really based on a short set of PFAS compounds. So one of the items that they're still trying to demonstrate is whether or not that works across the entire spectrum. But I'd say it's just it helps to be a reactionary compound within that airstream as it's passing through the oxidative state.
Okay. All right. Well, I'm not seeing any sort of, I think I've got at the essence of all the questions that have come in for Rob about thermal desorption. So I'm going to go back, and there's a few more for Rebecca here. We're wondering about in the world that's out there, virgin carbon versus reactivated carbon is like for a wastewater, I mean, not wastewater, for a water treatment facility. Is it mostly virgin that they're getting, or is it a mix? Is it mostly reactivated?
So if it's a new drinking water site, they'd start with virgin, and then I would say mostly would start to transition onto a custom municipal drinking water carbon. So it would be where we remove their carbon, take it back, reactivate it in batch process, and they get their same carbon back. So that would be for drinking water. I think a lot of wastewater is our industrial pool reactivated carbon, and they can basically start off with that product. It is its own unique saleable product. So I'm not sure if that covered both bases, but yeah, drinking water, you'd always start with virgin. Wastewater, you can go directly to a pool reactivated product.
Okay. So of the carbon that's out there, is a lot of it, is it more than 50-50 reactivated virgin, across all the uses, or is it?
Oh, that's really hard to say, only because there are so many different applications and then different industrial applications.
Yeah.
So yeah, I'm sorry, I'm not sure about that one.
Okay. I can't remember whether your slide had mentioned it or not, but there are reactivation sites in the US, but where are they? Were they on the slide?
They may not be on the slide. I think we had a map. I think I took the map out of this particular deck. So we have sites in Pennsylvania, Kentucky, Ohio, New York, and Arizona for reactivation.
Okay, so lots on the East Coast here. So folks, if I haven't gotten to your question, maybe type it in again if there's something that's burning that I haven't gotten to.
Well, if I could add one more thing, I guess, between the virgin and the reactivated carbon for wastewater treatment, if the target compound are PFAS compounds and it's low level, in most cases, the virgin carbon is has much better performance than a pool reactivated, just because of those differences in quality. So the reactivated carbon is still very high quality, but the pool react will not be the same quality as a virgin or as a municipal custom. So.
Okay.
Yeah.
Let's see. Yeah, people are very concerned about the off-gassing from both of these systems, from both thermal desorption and the carbon reactivation, but it seems like you guys have sophisticated air emission controls that are capturing that. Are we confident that we're not releasing PFAS to the atmosphere? I guess both of you can answer that.
Well, I will say that I think from an emitter's standpoint, the only way to be certain is to actually perform continuous testing, right? And in order to perform continuous testing, you have to be able to process and treat material. So as technology develops in relation to air emissions, the only way to continue to determine whether or not you meet criteria based on the testing that's available is to perform additional testing. So there's a lot of concern, in relation to various technologies. The emission side of it is really the crux of trying to get any science developed because of the concern in relation to emissions. My opinion.
Right.
But the only thing you can do is do what's best as available technology from an emission standpoint.
So is a fluorine mass balance, is that how we're going to figure out whether there's emissions happening, or?
I don't think, and if you ask EPORD, and I believe they've actually written this, they don't necessarily believe that a fluorine mass balance is practical or is actually the end all be all for PFAS testing emissions. As was noted actually in the Calgon presentation, I believe, and it's the same with our process, is that fluorine is highly reactive with some of the silicate-based refractories that reside within these systems. So those refractories can grab a hold and react with that fluorine and actually reduce the mass of fluorine that's actually generated or seen at the stack. So the concept of getting a full, complete mass balance in relation to fluorine, I think, is personally probably not practical.
Well, that's good to know. Because it's being retained in the vessel. Is that what you're saying?
Well, it's well, it can be. It reacts if it's an acid, as was referenced in I think both presentations, right? That acid can react with metals. The fluorine itself can react with the silicates that are in the refractories. So yeah, it can be within some of that refractory media. So.
And it can also be damaging to your equipment over time, I would imagine.
Yeah, but I would agree. But that's part of why facilities do continuing maintenance, right? Nobody starts up a process such as any of those ones that are being discussed, and from a thermal technology, which just tends to generally want to destroy things that you have to maintain them and keep them up. So.
Okay. Well,
I'll echo, agree with everything that you just said, Robert. Thanks for articulating that so well, and just echo that your process is only as good as what you can measure, and all you can do is keep up with the measurement systems as they continue to evolve.
Great. All right. Well, if either one of you have a parting message you want to get out, because we are pushing up against 3, so we'll be ending here. Does Rob or Rebecca have one last message? All right.
I don't at the time. Thank you.
Okay.
Nope, thank you very much for everyone's time today.
Great. Well, thank you to both Robert and Rebecca for your great presentations. Like I said, we'll be posting PDFs of them on the NMOA website, and I will send around an email when they are available. And so thank you again. once more to Robert and Rebecca for their great presentations. And I'm going to end the webinar for everybody and just enjoy the rest of this beautiful day. Well, it's beautiful here in where I am anyway. Bye-bye.